We're talking chapter 12 here. Chapter 12, kinetics here. And last time we got into the rate law. And remember that when we write a rate law, a couple of things important to keep in mind. The rate law looks something like this. For example, the rate's equal to k, a to the x, and b to the y. It only involves reactants. So when you write a rate law, again, it only involves those reactants, no products is sort of involved. Um, Also, they are found experimentally. So we do not just kind of get things from coefficients or anything like that. As we talked about, these are what are referred to as the orders of the reaction. And those obviously as well, they're found sort of experimentally, and they are not the coefficient in the balanced equation or anything like that. That is not how we get them. They may end up being the same number, but again, that's not how we get them when we're trying to solve for it. So as we saw last time, typically speaking, in these type of problems, you will be given some type of experimental table that typically will have, a number of experiments. Will typically have the concentration of your reactants in there, and it will typically have the initial rates of each of those guys in those experiments. And the idea here is we want to first sort of figure out our orders for our rate law. And we could do that really mathematically. We could again take that sort of formula, rate 2 over rate 1 equals our k, a to the x, and b to the y. And remember that what we're looking for when we do go to this table is to try to keep the sort of unknowns to 1. And what that means is what you would want to do is when you look at your reactants, you would want to find two experiments where pretty much, for example, let's say A stays the same concentration, but B varies. And that will allow you to figure out the order of B. Once you do so, then you kind of switch it up and do the opposite there. You want to find two more sort of experiments in that table, one where B is held constant and A varies, and I'll allow you to do that. In a rare case, if you do have more than just two reactants, maybe like three reactants, you would then want to, as we mentioned last time, make sure you choose two experiments where two of the reactants stay the same and one varies. Again, the idea here is just to have one variable so that you can solve for it. The idea of that is when you put your rates in, as we also talked about, if you want maybe prettier whole type numbers than decimal numbers, when you go to put what's on top there, you want to choose whichever experiment had the larger rate, and that typically will give you more of a whole number when you're all done. And again, you would put, for example, if I chose experiment 2 and experiment 3, and I'm just going to say experiment 3 had the larger rate, I would take all the information from the table for experiment 3 and put it up on top. I would take all the information from experiment 2 and put it on the bottom. And you do some math like this would cancel out and maybe give you a 4. Again, the rate constant here should be the same value, although we don't really know what it is at this point. It should cancel out. And we'll say that A was constant in this case, so the order X there should also cancel out. And that'll give you maybe something like, again, like maybe 2 to the Y. And here you would solve for Y, and if it's something you could just obviously figure out, you'd probably be okay. Again, because it is really based on experiments, sometimes the numbers aren't perfect and stuff like that. So you can, if you want to kind of clear it, thank you very much. If you want to clear it, you can take the natural log of both sides and then divide out like the natural log there to both sides and get you a 2 there going on. So that is the way we do that. Once we have the orders, we could write the completed rate law. And so whatever they end up being, again, we'll just hypothetically go with like a 1. Actually, we'll do none there. We'll do that and this. And remember that if nothing is written, it does represent 1, and we typically don't write 1. We can get the overall order at this point, which would be for this reaction 1 plus 2, which gives us third order. We can then, once we have the completed rate law with the orders, we can use the rate law here to solve for the value of the rate constant. And to do that, you just rearrange your rate law. You do, as we talked about last time, have to take into account, obviously, the orders there. And you could choose any entry you want in the table. They all should give you, again, the same rate constant, since it should be a constant value. And obviously, you want to be careful with the units as you go through there, because Again, different units on the rate constant will tell you sort of a different reaction that you're dealing with. Any questions on any of that stuff there? All right, so I think we laid up on this one, I think, if I'm not mistaken. So why don't you give it a go? Based on the information below, let's do obviously the completed rate law with the orders, obviously. We're looking for the overall reaction order, and also obviously the value of K in this case. So why don't you give it a go, see what you come up with here. Okay, so let's take a look. So once again here, we got 4 entries. We're going to try to find our rate law. So we can just start with kind of the generic rate law there. The rate is equal to KNO2, and we'll call that to the X, and we'll go with CO to the Y here. Again, we're going to use our table here to figure out the orders. So we'll start with finding 2 entries where one remains constant, the other one varies. For example, here, if we look at number 1 and number 2, those will stay constant. We also could have chose 2 and 4 and 1 and 4 as well. So you could have done those as well. Again, they all should get you pretty much the same number. So I'll go with 1 and 2 here. So if we go with experiment 1 and 2, again, just looking at 1 and 2, it does look like number 2 has the larger rate here. So I'm going to put that one on top. So number 2 is going to go up on top. We're going to go 0.0082 equals K. And we got 0.2 there to the X. And 0.1 there to the Y. Going to put everything for experiment 1 up on the bottom there. And that's going to give us 0.0021 K, 0.1 to the X, and 0.1 there to the Y. All right, so doing our math here, we're going to go 0.0082 divided by 0.0021. And go points. Helps if I put a decimal on the number, I suppose, when I punch it in there. 0.0021. I'm like, that looks like way too high. So that's going to give us like a 3.90476. Again, not a perfect number there. We do have those guys canceling out because they are constant. We don't know what this is at this point, but it should be the same, which means those guys will cancel out. And that's going to give us a 2 to the X. So again, you do have 2 options here. It's fairly close to 4. You can probably just round if you want. If not, again, you can just natural log both sides there. And that's going to bring the X down, and then divide the natural log there to the other side. And if you do that there, you will get basically that X equals 1.97 essentially, which is fairly close to 2 in this case, right? And again, if you rounded the original number to 4, you probably would have been okay in that case. But again, that's how you get it. Now, just to show you, if we did, for example, 2 and 4, we would have ended up with 0.033 divided by 0.0082 equals K. We'll go 0.4 to the X and 0.1 to the Y. And K 0.2 to the X, 0.1 to the Y. Again, in this situation, we would ended up with 0.033 divided by 0.0082. That again is not going to give us a perfect number here, 4.0244. It is experimental. Equals, again, these are going to cancel. These are going to cancel 2 to the X. Again, doing the same thing, taking the natural log of both sides there. And dividing it out is essentially going to give us R2 pretty much like we saw on the other one. Here we'll actually end up with actually a little bit over 2, basically like 2.01, which is again close enough to 2 in this particular case. So again, as I mentioned before, you may not always get, a lot of times the books they do kind of give you nice numbers that come out, but you may not always get it experimental. So you can do a little bit of rounding if you're close like we are. You should be okay. Yeah. Yeah, if you want, I would probably prefer just be on the safe side in certain situations, maybe just to do the natural size and round at the end of that if you're kind of close at that point, I would say. Other questions? All right, so no matter which one we chose there, we were doing it for NO2, so our X is going to equal 2 in this case. I got an extra page, maybe. Yeah, I do. So then we'll come back here to our table, and we're going to keep the NO2 constant. In this case, I think you just got one option, and that is experiment 2 and 3. So we'll go experiment 2 and 3 in this case. And once again, kind of looking at 2 and 3, we see they're fairly close, to be honest with you. So I'm still going to take the little larger one there on top, which is experiment 3. We're going to put everything from experiment 3 up on top. So that's going to be 0.83 equals K, or which was 0.22. Sounds good. And we got 0.2 and 0.1 in this case. So essentially, again, here, you essentially have got in this case 1, right? But again, if you divide it, you are going to end up a little bit over 1. So again, I would say in this case, you're probably good to just round it to 1. And that will get you here. These guys would cancel and give you 2 to the y. That means in this particular case, y would equal 0, right? Yeah. And again, if you're not sure, you can take the natural log of both sides and divide them out, and you'll get basically 0.01, which is basically 0. Yeah. So you'll basically get that. All right. So that is our order with respect to the CO. So we now can write our completed rate law. The rate is going to equal K. It was NO2, and that guy was squared. Now, remember, as we talked about last time, I think at one point, because this is zero order for the next one, you have really one or two options in terms of how you want to write the rate law. You can put CO, but as we talked about last time, you cannot leave it like that, right? Because that would imply that the CO has an order of 1, right? Because there's nothing written. So you definitely would have to write the 0 in there to indicate that it is zero order. The other option is because it really does equal 1, you actually can sort of omit it from the rate law and just write the rate law like the bottom one. But again, you cannot, as we talked about last time, just leave that kind of blank with no 0 written there. Otherwise, it would imply that the order for that guy would be 1. So you want to be careful on that. Other questions on that there? All right. Now, the overall order in this case would be we got a 2 plus 0, which is second order in this case. And now we're ready to solve for our rate constant. Once again, you could choose any entry in the table. I'll go with the first one there. And that's going to give me, when I rearrange this, the rate constant equals the rate divided by NO2 squared. So again, going to the table there, we got 0.0021 on top, and that is molarity over seconds. We have our concentration of NO2 there, which is 0.1 molar. And again, we do want to make sure we are squaring it. And that would get us 0.0021 divided by 0.1 squared. Oh, no, that's not right. Try that again. There's squared. There goes. Square that thing. There we go. And that's going to give us a 0.21, I believe. And in terms of the units here, basically a molarity on top and 1 on the bottom will cancel out, still leaving you 1 over molar seconds in this case, or again, you could do the -1 in this particular case. Those are, by the way, the typical units that we see for a second order reaction overall for the rate constant. And dare I say, like I said last time, that looks like 2 letters. Second order kind of works a little bit like that in most cases. Any questions on any of that there? Yeah. Wouldn't Y be? Uh, no, because anything to the 0 order will equal 1. Yeah. You know, you don't divide it. You actually have to take the natural log. So you'd have some natural log, basically 1.01 or 1 if you want, if you're rounding, and the natural log of 2, because that brings the y down. The y is up as a kind of an exponent at this point, so you have to do the natural log, kind of bring the y down to like a non-exponent number. And that is actually what you're going to be dividing. So you take the natural log of 1 divided by natural log of 2. Other questions? All right. Let's do one last one here. Just make sure. Same thing. Find everything that you need. Okay, let's take a look again. We're going to pick out a couple that stay the same. So I'll start with 3 and 4. That's going to keep the first one constant. Our kind of rate law we're trying to get to our orders here looks something like this. Little NH4 plus to the X, NO2 minus to the Y, if I squeeze in there. All right, so looking at 3 and 4 there. Once again, I'm going to go larger one on top. That is 21.6 times 10 to the minus 7, by the way, in case you missed that right about there. That's kind of important. If you did miss it, you'd probably be okay for most of the problem, but we'll catch up to you later if you missed that. So make sure you do look at the table there and some entries. Make sure you don't miss any type of values that you might need. We're going to go K 0.2 to the X, 0.0404 to the Y. Also for this guy here, we're going to go 0.2 to the X and 0.0202 there to the Y. All right, so doing our little math here. Going to get us a 2 is equal to, again, these are going to cancel, these are going to cancel, and that's going to yield us a 2 there. Y will equal 1 in this case. Now, coming back to our table, we're going to keep the other one constant, and it looks like we have just kind of one option on that one as well. It's going to be 1 and 2 to do that. So experiments 1 and 2. Once again, choosing the larger rate to put on top, which would be experiment 2 in this case. And again, we want to make sure we don't forget the times 10 to the minus 7 part is going to equal our K to the 0.06 to the X and our 0.2 to the Y. Putting everything from experiment 1 on the bottom, 10.8 times 10 to the minus 7, K 0.02 to the X, 0.2 to the Y. Again, here we got 32.3 to the minus 7 divided by 10.8 to the minus 7. Basically a 2.99, and I'm going to, again, round that to 3 in this case. And that's going to equal K, and these guys are going to cancel. And if we do that, that's going to equal 3 to the X, and X will equal 1 in this case here. Any questions on that there? All right, at this point, we now have our completed rate law. And we will have this, I think. And we'll have that. And again, they're both in the first order, so we don't need to really put anything there. It's implied that they're both 1. And that means that our overall in this case is going to be 1 plus 1, which is second order. Now, if you kind of miss this part here, this is where it's going to catch up to you, right? Because you're going to have the wrong number. You're going to be off by that factor. So we're going to solve for our rate constant. So our K will equal our rate divided by the NH4 plus and the NO2 minus. So once again, here you could choose any entry you want. So I can go with the first one. 10.8 times 10 to the minus 7 molar seconds. And again, that is definitely in this case where it comes important. And down on here, we're going to go 0.02 molar and 0.2 molar in this case. And if we do that there, 10.8 to the minus 7 divided by 0.02 and divided by 0.2. Gonna get us something with too many zeros to count right now, but we'll go 2.7 times 10 to the minus 4. Unit-wise, a molarity up on top and 1 on the bottom will cancel, giving us the same sort of units we saw in the previous one there, 1 over molarity seconds, which again is the typical units for a second order reaction. Questions on any of that there? So clearly you need to be able to, if you're given the information in a table, come up with the orders for everybody, the completed rate law, the value of the rate constant, and the overall ordered reaction. Any questions on how to do that there? All right. Then let us talk about specifically different types of ordered reactions. So the first common sort of reaction we're going to talk about is what is known as first order reactions. And first order reactions are one of two ways. You could have a product or a reactant go into a product, which we can write the rate expression for, and also the rate law, which is the rate is equal to K times the concentration of A. Now you could get this with one reactant, where obviously the order of the one reactant is first order. You could also get this with two reactants, where one of them is first order and the other one is zero order, right? So it's possible you could have two as well. The common sort of orders of reactions we're going to talk about is first order, second order, and zero order. Because again, if you think about most, for example, reactions that you probably have seen, I would say probably in most cases, one or two reactants are essentially the most that you kind of typically see in a chemical reaction. Occasionally you see three, but you typically don't see, for example, reactions that have like, 4 or 5 things reacting at once or something like that. So these end up being because of, it's usually like a combination. They made one thing reacting, two things reacting, occasionally three things reacting. The common orders overall for reactions that we see are first order, second order, and zero order. As if you had, like a 20th order, you would need a lot of things kind of happening sort of at once. And obviously it doesn't usually occur that way. Now, if we take the rate law like we have over here and we actually solve for the K and just look at the units associated with it, what we will see is one of the first important things that you should remember for a first order reaction is the units that are associated with a first order reaction for the K value. So the rate constant should typically have 1 over seconds or 1 over reciprocal seconds. To be truthfully honest with you, that is probably the most common unit that you'll see for first order, but it does not have to be seconds. So it's really 1 over some unit of time. So it could be seconds, 1 over minutes, 1 over hours, 1 over days, weeks, whatever you want to do there, years. But most of the time, if you just think about experiments you would do, you probably be measuring seconds, right? And not like days or weeks or years and stuff like that. So it can technically be 1 over some unit of time. Most commonly what we see in sort of chemical reactions is 1 over seconds is the common sort of unit. For example, when we talk about nuclear chemistry and radioactive decay, which happens over years and years and years, the typical units that you see for that type of one is like 1 over weeks or days or years, because it does occur over a long period of time. Why is that important? As I might have mentioned last time, there will be problems that you'll come across where they will not in blinking lights tell you, hey, it's a first order reaction, right? And they're just going to give you the value of the rate constant, and they'll give you it obviously with the units. And they assume that once you see those units, you'll understand that it is the first order reaction. And why that's important is, as we'll see here in a second, there are specific sort of formulas that you would use for a first order reaction that you would not use for a second order and vice versa. So speaking of that, there is a typical graph or a couple of typical graphs that we see for a first order reaction. This graph here is just concentration over time. And what we typically see in a first order reaction is it should start decreasing with time. So as that reaction is happening, we'll see this sort of decrease with time. Kinetics, though, especially kinetics, is all about sort of linear relationships and best fit sort of relationships. So if we take this sort of concentration and time equation and go through and natural log it, we get what is sometimes referred to as the integrated rate law, which is this guy right here. And that is the integrated rate law that basically deals with concentration and time and how everything changes. the natural log of A is equal to the natural log of A naught minus KT. So the A here is like our final concentration, if you want to think about it that way. Our A with the little knot on the bottom there is our initial concentration. The K here is our rate constant. And sometimes people mess this up until they get used to it. It is a lowercase t, which is actually time, not temperature. Yeah, so that is time, not temperature. Again, temperature, capital K, right? Capital T in that case. So when we take this integrated rate law, you could actually rearrange it and write it like this, that the natural log of A is equal to minus KT plus the natural log of A naught. And when you rewrite it like this, that is in the form of a straight line, or y is equal to mx plus b. So what that tells you is the typical, although this is a first order sort of plot, the typical first order plot that you see is actually the one over here on the right. And that means on the y-axis there, I will have the natural log of A. And on the x-axis there, I will have time. And it will give you a linear relationship, as you can see here with this. That is, by the way, a positive sloping line or a negative sloping line. That is a negatively sloping line, right? Positive would go that way. Negative. Think of like a number line right there on the middle, pointing towards the negative side of the numbers, right? Or the positive sides. So that's a negative sloping line. So we could actually find the value of the rate constant graphically by taking the slope of that line. So the slope of that line is actually equal to not K, but it's equal to negative K. Yeah. And that negative that's there, along with the negative value you would get for the slope, will turn those two negatives into a positive value for the rate constant. So again, your rate constant should be positive when people do it, especially in lab. When people do this experiment we're going to do next week, we'll start. They always want to end up with negative rates and all that kind of stuff, or negative rate constant. But again, that's why there's the negative here in that sort of relationship, and your slope line will be negative. So those two should turn everybody into a positive number when you do it. Now, there is a half-life equation we'll see down the road, but I'll just put it here. The half-life is equal to the natural log of 2 divided by the rate constant. Natural log of 2 on your calculator is 0.693. You'll sometimes see it written. What is the half-life? It is pretty much what the name implies. It is the time it takes for half of whatever you started with to go away, basically, right? So that is your half-life. That is also why we'll talk about in a later chapter when we get to nuclear chemistry. All radioactive decay follows first-order kinetics, so it kind of follows this type of decay. So a couple of other important things when we look at these sort of equations as well is you do want to be really careful with this part of it here, and that's also obviously the same thing here. And the thing that you want to be careful with is the rate constant for a first order is 1 over some unit of time. And obviously time is a unit of time. Now, sometimes the unit of time in each of those are different units. Like maybe you have days in one and like weeks in the other, right? So you just mathematically want to make sure the unit of time in your rate constant and the unit of time in the actual time value are the same units, so everything cancels out. The other thing that sometimes you'll come across is you sometimes will have to use both of these sort of formulas together. So you'll sometimes have to use both the integrated rate law, whichever one you want to use, and the half-life sort of formula together, because in some cases they may not give you the value of the rate constant, but they may tell you the half-life of what's going on. So you would use the half-life equation to figure out the rate constant, and then you could go into the integrated rate law and solve for what you're really looking for. So very commonly, you sometimes have to use both of those formulas together. I would say probably when we get into that nuclear chemistry chapter, a little bit more of that will happen. We kind of have to use them together, but you potentially could have to use them together. All right, so this is a first order reaction, so important stuff to know, obviously, right? K and the units, the integrated rate law, the half-life equation, and the graphs that are associated with it. Again, really, this graph is probably the one you're going to see the most questions on that there. All right, so let's take a look at one. Why don't you give it a go? The reaction of 2A goes to B is first order in A. With a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds, how long will it take for the concentration of A basically to go from 0.88 molar to 0.14 molar? So give it a go and see what you come up with there. So obviously, this is first order because they were nice enough to tell us. But if they were not nice enough to tell us, we would know that this is first order because they did give us the rate constant and we see those units, right? So that right there again tells us it's first order. Because it tells us first order, that takes out our equations or formulas that we could use here for specifically first order reactions, which is our again concentration versus time dependency. I don't think we'll need the half-life since nothing was mentioned, but this is also obviously in play as well. So we obviously have K given to us, which is 2.8 times 10 to the minus 2 reciprocal seconds. We have the initial concentration of 0.88 molar. We have our final concentration there of 0.14 molar. So we really do have everything we need to solve for time, which is what we're looking for. So that's going to give us the natural log of 0.14 equals the natural log of 0.88 minus our 2.8 times 10 to the minus 2 reciprocal seconds, and that equals our time. Now, personally, what I would do mathematically is I'd take on my calculator the natural log of 0.14. I would hit equals and then subtract this guy over to the other side. So I'm going to go natural log of 0.14 hit equals, then subtract the natural log of 0.88. And that's going to get me minus 1.838279485. Don't feel like rounding. It gives me minus 2.8 times 10 to the minus 2 reciprocal seconds. At this point, I'm going to divide this to the other side. And not only that, but I'm also going to take the negative with me. So that's going to turn my time into a positive number, which would probably be good. Yeah. You probably don't want negative time. Yeah. So if I do that, we'll call it about 66 seconds. By the way, that's reciprocal seconds, but when you divide it, it comes to the top, right? And we end up with our time of about 66 seconds, about a minute or so there for that to drop. Any questions on that? Yeah. All right. So as I sort of jumped a little earlier there, the half-life, again, is that time it takes for half of whatever you have to go away. And specifically for a first order reaction, that is the half-life equation, natural log of 2 divided by K. You could get that by essentially, if you could derive it yourself if you needed to, by doing the initial divided by 2 for the final concentration, solving for T. So, if you're bored one day and you want to do that, basically you could take the first order reaction here, our formula, and for this, the half-life would be our initial divided by 2, and then solve for T, and it'll eventually get you down to this guy over here. Or you could just remember it and not have to worry about doing that. All right, so what is the half-life here of our N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4? Okay, so putting this in, we have our half-life equals the natural log of 2 divided by our rate constant. They gave us the rate constant here of 5.7 times 10 to the minus 4 reciprocal seconds. And that's going to get us there. Looks about like maybe 1216 seconds or about 1200 seconds you're still interested in significant figures at this point. We know, by the way, that we should be using our first order half-life because of the units, right? So the units that we see here is the reason why we know it's first order, and we should use that because the rate constant, right, has those proper units for first order. Any questions on that one there? Yeah. All right, so as you can see here again, half-life as we drop down again is how much is left over, or half of it's left over the time it takes for that to happen. After about 10 half-lives, you probably got not much left over at that point. I'm going to try another one here. The reaction is first order with the rate constant. Find the concentration of SO2Cl2 at 865 seconds if we started with 0.0225 molar of it. So we're looking for the final concentration here. Nice enough to tell you, but for most part, they're not nice usually. But once again, we can definitely figure out what order we're dealing with based on the units of the rate constant, which again are reciprocal seconds. So again, that should definitely point you in the first order direction. So again, we'll go with our formula here for first order. And I will just kind of pull out some information here. So we got K is 2.90 times 10 to the minus 4, I think, if I didn't scribble too much on it. We are looking for really our final concentration. They did give us our initial concentration of 0.0225. And they also gave us our time here of 865 seconds. So we basically have this, this, and this, and that's really all we need. We do want to just make sure, and as I was talking about earlier, we're okay in this case because, again, the unit of time on our rate constant and the unit of time here on the time value are the same units of seconds. So again, if those guys were different, you do need to do, it doesn't really matter which one you would convert, but you do need to convert them to the same units. So we could go in here, natural log of A, natural log of 0.0225 minus our 2.90 times 10 to the minus 4 reciprocal seconds. And I'll try to squeeze it in there, 865 seconds. Cleaning up everything on the right-hand side, I'm going to go natural log of 0.0225 minus 2.9 to the minus 4 times 865. That's going to give me the natural log of A is equal to minus 4.0450997 if you don't do any rounding. To get rid of the natural log on the left-hand side, I need to E both sides. Yeah, so I got to take the E there to both sides. That's just going to get rid of the natural log on that side, and that will leave you your A. And do that little move there. And perhaps a 0.0175. The units here are is going to be molarity, just like the other unit. And we do need a unit because it is a concentration, so we do have to put that unit back in. Question on that one there. It does, yeah, did you have a question? That is the, this one here? That's the equation for the first order that we saw on the slide where we looked at first order. Yeah, it was right above the graph there on the bottom right corner. Yeah, and I wrote it on top as well, I think. Yeah, but that's the specific is what's known as the integrated rate law for concentration and time dependence of each other for a first order reaction. Other questions? We also see, right, our final concentration is less than, right, than what we started with, right? So it should be decreasing with time. So if you do something like a calculation, you end up with more than you started with, you're definitely going in the wrong direction, probably. It should not be doing that. All right. I think we may skip that. Yeah, we'll skip that one, I think. And we'll do it real quick. We'll just do it together. So what is the half-life? Obviously here, we have the rate constant. So once again, by seeing that for our rate constant, that should direct us to our half-life equation for our first order reaction. And really in this case, we just got to pop it in there. So natural log of 2 0.271 reciprocal seconds, and putting that in there, that's going to give us about 2.56 seconds as the half-life. So that reaction is moving quite fast. Yes. So every 2.5 seconds, half of what you started with is gone. Yeah. So it's moving at a pretty good rate there, right? Obviously, if you have a larger half-life or a bigger half-life, it's moving maybe a little slower, that reaction, right? Than if you have something that's moving pretty quick. All right, so that's first order. As I mentioned before, the other two sort of common orders of reactions are second order and zero order. So let's take a look at second order reactions here and what we got going on with that. So for a second order reaction, you basically could get there one of two ways. You could have a two reactants where each one's first order, and that will give you an overall second order reaction. You could also have two reactants where one is second order, one's zero, like we did on a previous example. And you obviously could have just that would probably be most of your cases, a single one that's second order as well. Now, just like we did with our first order, if we take the rate law here and solve for K and look at the units associated with a typical second order reaction, we do see different units than what we saw with our first order reaction. So the typical units of K are 1/molar seconds. Once again, the time part of that does not necessarily always have to be seconds, but it should be some unit of time. It can be seconds, minutes, whatever it may be. But again, in a lot of cases, it will be seconds because that's a common sort of unit. So again, this is how you do want to remember, obviously, the units associated with it. This is how we could distinguish it from, say, a first order reaction. If we're given a problem where they don't tell you what order it is, right, by the units that we see with the rate constant. So these units associated with the rate constants are really important in terms of understanding what type of reaction you're dealing with so that you essentially will use the right formulas to do the calculations. Now, we do have an integrated rate law for our second order, and it is this one right here. It is 1/A is equal to 1/A naught plus KT. And we can rearrange that formula just like we did the first order one, like so here, KT plus 1/A naught. And this would be the second order sort of formula rearranged in the form of a straight line. Y is equal to mx plus b. Once again, that will give us the typical graph that we see for a second order, which is on the y, 1/A, and on the x, our time. This again is going to yield you a straight line. The difference, though, between second order and first order here is we actually have a positively sloping line. And that means that when we take the slope of that line, it is going to just equal the rate constant. So there's no negative in this one. We don't need it because our line is actually positively sloping in this particular case. We also end up with a different half-life equation. And the half-life equation here is actually 1 over the rate constant times the initial concentration. So unlike, for example, first order half-life equation, which is the natural log of 2 over K, the first order has nothing to do with the concentration initially. This one is affected or it has a bearing on the initial concentration, right? So this one will be affected by the initial concentration. Just logically speaking, if I end up with a really large initial concentration, my half-life will be larger or smaller than somebody with a smaller one. Just mathematically, if I put a really large number on the bottom, what do I end up with? If I take 1 over a large number. Yeah, you end up with a small number, right? As opposed to if I took, 1 over a larger number. Just for example, if you took like 1 over 50, right, versus 1 over 600, right? The 1 over 50 is 0.02, right? The other one is like 0.000, right? So If you have a larger initial concentration in a second order reaction, your half-life will end up being smaller, right? And actually quicker, right? And if you have a smaller one, your half-life will actually be longer, right? And that makes sense if you just think about it logically in this case, right? Because you have a greater concentration, probably half-life's gonna be quicker because you're gonna be able to find each other quicker, right? As opposed to a smaller concentration can take longer, right? For everybody to find each other. So once again, much like our first order, there are several things that you do have to know for second order reactions. Definitely those units associated with it, so you can recognize if it's not told you, are kind of concentration, time, integrated rate law, half-life, and again, our typical graph that we see for our second order reactions. Questions on that there? The last sort of common one that we're going to talk about are zero order reactions. And zero order reactions basically can be happening, pretty much one way for the most part. You have a single reactant that has an order of 0. And because of that, if you write the rate law, and we know that something to the 0 order is 1, that basically means that the rate's equal to k. So that gives us the important information when we see a rate constant that has units of molarity over seconds. We know that that is typically for a zero order reaction. And again, it'll basically have the same units as the rate constant. We also have some integrated rate laws here for zero order, and it is our A is equal to our A naught minus KT. And again, everybody here is the same as in all of them. Just like the other ones, we could rearrange this and write this in the form of a straight line, and it looks something like this if you do that. And again, that's going to be our y is equal to mx plus b. So once again, the typical graph that we see is the concentration on the y, time on the x, and that is going to yield us, once again, a negatively sloping line. And just like kind of with first order, the slope of that line will equal minus k. Again, for the same reasoning, we have a negatively sloping line. The negative value that you would get for the slope, along with the negative in the formula there, gives us a positive value for k. Now, you may say to yourself, isn't this the same graph that we saw for first order? And the answer is, it is the same graph in the sense of what you were graphing, but they do not look the same. So if you have the exact same thing graphed here, the concentration of A versus time, and you do not get a linear relationship, but you get this more decreasing with time relationship, that is first order. It's not, again, a linear relationship. If you get a linear relationship like this, it is definitely zero order. So like I said, a lot of times, though, the good thing is a lot of times people will not kind of use this for the first order graph. So, but it can still pop up. So again, if you see that and you go, that kind of looks like the zero order, but it's not linear, it may be a first order graph you're looking at. Or if obviously it should be linear, it is a zero order sort of graph in this case. We have a half-life equation as well here. So much like the second order, our half-life here is the initial concentration divided by 2K. So once again, the half-life here is affected in a zero order reaction by the initial concentration as well. Just like the others, there main things to remember for our zero are units there of K, our integrated rate law, our half-life, and again, the typical graph that we see for a zero order. I would say a lot of times people mess this one up with first order, yeah, and they can't remember which one has the natural log and which one doesn't. So just try to keep that straight. Any questions on that there? All right, let's try one more here. Maybe the reaction of Q goes to 2R is second order in Q. If we have an initial concentration of 0.01 after 50 seconds, the concentration is 0.001. What is the rate constant? Okay, so since we're getting there, let's take a look at it here together. All right, so obviously they tell us a second order, so that should automatically take us to our second order sort of formula here. Remember, this one is plus KT. Um, and in this case, we have our initial concentration of 0.01 molar. We have our time, which I misspoke earlier, is 500 seconds. No, it's kind of like 50 if you had an extra zero. And we have our final concentration there, 0.001 molar. So we really do have everything we need to solve for K here. So that's going to give us 1 over 0.001 equals 1 over 0.01 plus K. And our time here being basically 500 seconds. Again, I'm going to basically take 1 over 0.001, and then I'm going to subtract that to the other side afterwards. So 1 divided by 0.001 gives us 1,000 minus 1 divided by 0.01. That's going to give us 900 equals K in our 500 seconds. And this is basically, we will then take our 500 to the other side. There we go. Hit it there. And that's going to give us a K is equal to 1.8. The units here, again, this when we divide it, we have 1 over molarity on that side. So when we divide our seconds, it ends up down there as well, giving us our 1 over molar seconds. As I was a little bit better there, I put my molarity on each of those there, right? So we have that going on. Question on that one there. All right, we'll lay it up there for today.